It's Scat,
and Caitlin.
and today we're going to talk about
Ionic bonding, type 1 and 2.
ionic bonding with an acid or base,
Covalent bonding, type 3.
valence electrons and how they relate to each bond,
And periodic trans.
So, a lot of y'all are sitting here thinking, what is ionic bonding type? I don't know. It's when a nonmetal and a metal transfer electrons, and
they bond together and they form this bond like two people bonding over friendship, like us. And transferring, if you're wondering what that is, transferring is when you take an electron from one element and you transfer it to another. So, for instance, nonmetals will gain and metals will lose. Like,
as an example,
lithium, which has a valence electron of 1, so it's +1. And then there's iodine that has 7 valence electrons, so it has an anion of -1. Take it away, Scott.
So, in this example, you crisscross these little things right here in digits, and these numbers, and you get Li1 and I1, which is the same exact thing as Li. Notice how this is lowercase I, and your second element would be capitalized. Also, when you're naming this compound as lithium iodine, it would actually not be iodine. The iodine changes to an iodide. Big little IDE change right there.
And the key to this is your equation. Your equation, because it's the +1 and the -1, will look like this. You'll put your +1 in parentheses, you'll want to add it, put your -1 in parentheses. Your goal is to get it to equal 0. So if you're lucky, like we are in this case, it already equals 0. So because this equals 0, you don't have to add any more of either of the elements. But sometimes you get unlucky, very unlucky, and you get things like aluminum and sulfur. And aluminum and sulfur, aluminum has a +3 charge, because it has 3 valence electrons, and sulfur has a -2 charge, because it has 6 electrons. As you can notice, if you were to put these in your equation, +3 plus -2, you would not end up with 0, but instead you would end up with 1. So now you have to figure out how you're going to make this equal 0, so you're going to take these two, and you're going to figure out what you can multiply them each to get the same number. So if this lowest number is 6, so you want both of them to multiply to 6. So you're going to put up 2 outside of 3 because 2 times 3 equals 6, which I hope to God you know, and 3 outside of 2 because 3 times 2 also equals 6. What a coinky dink. Anyways, this is going to give you 0, so this means that you're going to need 2 aluminum elements and 3 sulfur elements. They're going to transfer to each other, and these are going to become one happy element, and it's going to look like
0.
L2S3, which would be aluminum sulfide. Keep in mind, kids, it's I and not er.
Bonus round!
Bonus. Okay, bonus. Okay, so if you wanted to do, these are all the bunches. We have these wonderful polyatomic ions. If you no longer feel like just a few, if you don't feel like adding another element, don't even sweat it. You'll just add some polyatomic ions. For instance, if you wanted to do sodium, which would be Na +1, and then you wanted to do nitrate. Let's go with nitrate. This has a -2 charge on it. Okay. Well, because nitrate has a -2 charge, you have to add 2 sodiums. So that's going to be Na2SO3.
Also notice how in nitrate, SO3 is the whole thing in nitrate. 2 is just a charge, and the 3 always stays with the SO. So you cannot separate the SO and the 3.
So for example, if you have something, and you have something that might have a greater charge than this one, for instance, let's go with calcium, which would be Ca +2, and you want to do nitrite. Nitrite only has a -1, and you need a -2. Well, problem solved. Ca, parentheses, this is key guys, don't forget your parentheses or you will get an F. NO2 in the parentheses, and you'll put a 2 outside. This is telling you that the entire thing is being multiplied by 2. If you just put this, if you just multiply this and this, you get 4, and you have 4 oxygens, and honey, that's not what you want.
That is wrong.
So remember, parentheses, when you want to have more than one polyatomic ions. Topic number 2 would be ionic bonding type 2. What do you know? So ionic bonding type 2, very similar, still going to be transferring, non-metals still going to be gaining, non-metals still going to be gaining, and metals are going to be losing, except this time your metals are transition metals. And these fellas are going to look a little funny, but you'll get the hang of it, I have faith. So let's say, since your transition metals are all these little things in the middle, we're going to take copper, or cobalt actually. We're going to take cobalt instead of copper, which is CO. Now, when you see cobalt, it's going to be written like cobalt, C2, or maybe there will be a 3 or a 4. It's going to be written like that. That's telling you that this element right here has a charge of +2. So if you want to take cobalt +2, you want to mix it with some sulfur, which is -2, this works out perfectly because it'd be CO, C, little o, S. And that is how that works.
Cancel out.
Now, the problem here is you're not always going to know what that number is in the parentheses. So if you're just given a Cu,
That's copper.
Cu, As, and you're just like, what the junk? You're supposed to write the size name and be like, what? I can't do that. Well, honey, you can. Because you know that these clearly have to be equal numbers because there's no numbers involved. And that As has a charge of -3. So this means that Cu, which is copper, would have to have a 3 in the parentheses since they perfectly match up. And this is ionic bonding type 2.
Bring on! Need help with my homework. I don't know what this thing is right here. Naming an acid is some H2SO3
Well,
thing. I don't know what it is. Help me.
Remaining acid and bases can be quite tricky. But once you get the hang of it, it's easy.
I don't think it's easy. Great ball. Really hard.
Shut up, child. I'll help you. Okay, now. So when you name acids and ions, just remember that acid will always have hydrogen in it. 9 contain oxygen?
Yeah, Grandma sure do. How do you know that? Right there.
Okay. And now you're going to ask yourself, you're going to say, what ending does my anion name have? Does it have an ice ending or an eth
Yeah,
ending?
have the sulfite up in there somewhere. Sorry, write a D. I still can't remember my T's and D's. They look like the same thing. I don't even know which one's which.
Well, since your thing has an ice ending, you're going to use an OUS. But now remember, when you're writing this, you don't want to write hydro.
Yeah,
You're
it's
just
too long
going
to
to
do. I
write
don't even know how to spell
sulfurous acid.
it. Looky there.
And that would be your answer.
Oh, thanks, Grandma.
But the thing is, kids, if you had an AT and E ending, you would use the root ic. So if you had sulfate, you would have sulfuric acid.
Well, how come you keep the UR in there? Why don't you just get rid of that too, Grandma?
Because it sounds better. I was thinking better education.
No, I don't need one. Got me
Now the question now is, what if you don't have oxygen in there?
I don't know, Grandma. They're too hard for me. I can't even
So
concentrate
what if you
right
had
now.
H2S?
I don't know. These get hard. Grandma,
God, you're taking this too long. Okay, so you're gonna find out that the answer no, you don't have oxygen in here because no one sees oxygen in there unless you're a man.
I think I see one right there.
Now you're going to add hydro to the beginning, and then it's going to say sulfuric. And it's going to be one long word. Then you have acid. And that is how that happens. You are welcome.
Thanks, Grandma.
Whenever you're deciding how you're going to name it, H, you're going to name an acid. OH, you're going to name a base, okay?
Covalent bonding type 3.
Type 3, remember that. It's 1, 2, and 3. Okay, so covalent bonding type 3, there's two major differences. You're not going to be using metal whatsoever in this. So don't even think about using metal, like at all. You're going to use a non-metal and another non-metal, okay? So because you're using a non-metal and a metal, these two are not going to transfer in. They're going to be sharing. They're going to share like this.
Like I share my food with Caitlin.
Exactly. Our first example is going to be hydrogen and oxygen, which is H2O, which everybody knows is water, okay? So here's hydrogen, the first one. This one little happy little electron, except for he's not so happy because he wants someone else.
Who's your friend?
Our other hydrogen with his lonely electron. And here is our oxygen with our 6 electrons. 6. Well, hydrogen and oxygen is gonna share with these guys. So they're little
They're
circles.
friends.
Their little circles are gonna connect like this. And they're gonna share 2. Because that means his octet is full. This means his octet is almost full. Now he's gonna share again with this hydrogen. It's gonna be that. There's gonna be 2. So now oxygen's full, and so are these two hydrogens, because they each have 2, and this guy has 8. And they share, and it's gonna move around. After they bond together, they're gonna move around like this. And they're gonna be happy, and they're gonna be wonderful, and now they're bestest of friends. So remember, covalent equals sharing. You're gonna share when you have covalent, because they don't want to give away. Non-metals are friends, and they enjoy sharing. So in topic 5, we're gonna talk about how valence electrons have everything to do with bonding. So valence electrons do have everything to do with bonding, because valence electrons are what bonding is all about. So for instance, type 1 for ionic bonding, you're going to show how you transfer these, because as if you do an ionic bonding type 1. And we're going to show you this process on the Lewis blot. So here's beryllium. He has 2 valence electrons, and oxygen has 6. So beryllium has 2, and oxygen has 6. And if beryllium just transfers his 2 valence electrons to oxygen, then they're both going to have full octets. And this is going to make each of them extremely happy. So you can see here, transferring, not sharing, giving them away, to the point where he gives them, he gains them, these are gone, and he's all happy. They're so happy.
Just like
Now-
Caitlin and I are happy.
Now we're going to show you ionic bonding type 2 and how those involve valence electrons. Similarly, it's basically the exact same thing, except for you're going to use transition metals. So we're going to use nickel and chlorine, and nickel has 1 valence electron, and chlorine has 7. Okay? So because nickel has that 1, and chlorine has 7, nickel wants to get rid of that just one little one. And then chlorine wants to gain just one, so they can both become full octets. And so nickel gives his to chlorine, bye-bye to that electron, and now both of their valences are full. Covalent bonding involves valence electrons. Similarly enough, they still have valence electrons, and we're going to use hydrogen, which has just 1. Right here. He's 1 valence electron, and he just wants another one to share with someone. And so chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Chlorine and hydrogen want to share these, so they're going to come together like this. Okay? It's not carbon, so they're going to sharing these 2. So they're going to run around, and they're going to enjoy the world, and they're going to enjoy the world together now.
So we're going to talk about atomic radius and how it has to deal with valence electrons. So when you look at a periodic table, this will be your columns, and this will be your period, and here will be hydrogen, and that's the first row, and over here will be all your known gases, and helium. So, and everything in between. If you're dealing with valence electrons and the atomic radius, if the valence electron, it has a tight attraction, and it's pulled closer to the nucleus, which allows it to get smaller. So as you can see, as you go from hydrogen to helium, the atomic radius decreases and gets smaller. Now we're going to talk about ionization energy. Woo! Okay, ionization energy is when you remove an electron from the outermost shell. So as you can see here, here's hydrogen, there's helium, and as you go down the periodic table, it decreases, and as you go over, it increases. So here are the metals, the semi-metals, and the non-metals over there. So as you can see, in the metals, there's a little energy, and semi-metals, it increases, so there's more energy, but then in the non-metals, there's a lot more energy. But now we're going to talk about electronegativity, and that is when you go across the periodic table and you gain electrons.
And as you go down, it'll really just stay the same for valence electrons, because as you start over, each time it'll be 1, 2, 3, 4, so on.